Good evening, ladies and gentlemen, and welcome to Mr. Salcedo's YouTube videos. Today, what we're going to be looking at are redox reactions. Specifically, we'll be looking at oxidation numbers. So this was originally one video that I had to break apart. So hopefully you watched the oxidation reduction kind of electrochemistry terminology stuff already so that it makes a little bit more sense to you. But if you didn't, hopefully I'll get you guys caught up anyway. But a redox reaction is any reaction where an electron or electrons are being transferred between the different substances. So if you take a look at this is actually an example of a redox reaction. Whereas most of the time people would look at this and say, okay, yeah, it's a synthesis reaction and leave it at that. But in reality, we have electrons that are being transferred here. And if you remember from the previous video, we showed what was happening with the chlorine turning into chloride and what was happening with the sodium solid turning into sodium ions. So in reality, this is a redox reaction. If you can remember back, it's just now when you put it together, it looks like, oh yeah, it's just synthesis and that's about it. So like it says here, how could we tell? Well, we could look at the oxidation states or we could look at the half reactions. If we look at the oxidation states of these two elements are 0. Chlorine as a gas is 0. Sodium is also going to be 0 when it's a solid. But when it forms sodium chloride, we have Na plus 1, so it becomes more positive. And then we have Cl minus, it becomes more negative. So if you remember back, we said that Cl2 to Cl minus, that would be an example of reduction. Whereas Na going to Na plus, that would be an example of oxidation. So like it says, what is oxidation state? All it is a fancy term for charge. So obviously we can see here the charges on these are 0. The charge on this is a plus 1. The charge on this is a minus 1. That is using oxidation states to figure out what's going on. The other thing that you should have noticed is that I said, oh, let's only look at half of this reaction. Let's look at just the chlorine and then the chloride. Let's look at just the sodium and then the sodium ions here. So by doing that, we're actually breaking it into two pieces. We're breaking it into a reduction part with the chlorine, and we're breaking it into an oxidation part with the sodium. So in reality, this is just kind of like a way of figuring out whether a redox reaction is happening and how it works. And there are two different ways of doing it. Like it says in the next Roman numeral, we'll look at both of these methods and why they're useful. But for now, all we really care about is this oxidation state stuff. So oxidation states, what are they? An oxidation number is a number that's assigned to an element or an atom, right, that indicates how easily it is oxidized or reduced. Now, it's mostly like a accountant's trick to keep track of all of the money that's going in and out. Instead, what we're looking at here is all of the charge. We're looking at the positives and negatives. We're looking at the electrons. We want to make sure that we're keeping track of all that stuff. So in reality, there's just a list of about 8 rules. Now, if you take a look at more detailed oxidation number rules, yes, there are probably more than this, but these are the only ones you need to know for situations that we will come across. So the first one is the oxidation number of any uncombined pure element is always going to be equal to 0. So in our first example, that would be Cl2 and Na, right? Those were pure uncombined elements, and that's why their oxidation numbers were defined as 0. What about monatomic elements? Monatomic ions, they're always equal to their charge. So Na plus, that means that since it has a plus 1 and it is only a single ion or a single element that is forming an ion, that means that that's also going to be its oxidation number, plus 1. Cl, that was Cl minus, right? That's a monatomic ion, just one thing. That's going to also be equal to its charge, so it's going to be a minus 1. Fluorine is always a minus 1 when it's in a compound, no matter what. H is going to be a plus 1. In our class, it will always be a plus 1, but occasionally when there are hydrides, it's a minus 1. But we haven't really dealt with hydrides for the most part, so you really won't see any hydrides now. Oxygen's usually a minus 2, but on occasion it can be a minus 1 if it isn't a peroxide, but we don't really deal with peroxides. So again, for our situations, it's always going to be a minus 2. The oxidation number of other main group elements matches their charge. So like aluminum in a compound would be a plus 3, magnesium would be a plus 2, lithium would be a plus 1. It's just remembering your charges of your ions still. Now, oxidation numbers for neutral compounds must equal 0, and the oxidation numbers of polyatomic elements in a compound have to add up to the charge of that ion. So if I have sulfate, SO42 minus, the oxidation numbers of my sulfur and my 4 oxygens has to add up to -2, since that's the charge of the ion itself. All right, So using those rules, let's do a couple of examples. So we're going to just look at the nitrogen in these compounds because the nitrogens in these compounds have different oxidation numbers. So first, we have N2, the simplest, right? Just nitrogen gas, a diatomic gas. So our very first rule says that if we have something that is a pure element, that is going to have an oxidation number of 0. And so that means that N2, the nitrogens, have to have an oxidation number of 0. Notice all of these are neutral compounds. None of them have a little charge have a charge for an ion or something there. So that means that all of these will have to have numbers that always add up to 0. And the only way to add n up to 0 here would be if both n's were equal to 0 to start with. Okay, next, N2O. So I know O is a -2, and I have two n's. That means the two n's have to add up to a +2 charge overall, which means a single n would be a +1. Remember, it's asking you what's the oxidation number for a single nitrogen in each one of these compounds. What about here? We have H, that's always a +1. We have 4 of them. That means this would be a +4 overall. That means that I have two nitrogens that have to make up that charge, so it's going to be a -2, right? So if I have two -2s, that's a -4. +4, everything's balanced. Next, H3, +1, that means I have a +3 charge over here. I have to have a -3 charge over here. What about over here? I have a -2 for my oxygen, so that would mean a -4 overall. That means this nitrogen has to be a +4 to balance it out. Oxygen here, -2. This one's kind of easy. That has to be a +2 then to balance it out. What about nitric acid? So I have right here a -2. That's a -6 overall. Now this is a +1, so that's a +5 overall, which means that now I need a +5 for my nitrogen in order to balance it all out. Same thing here, right? I've got a -2, that's -4 then overall. I've got a +1 though, okay? Which means this would have to be a +3 in order to balance everything out. So notice, here nitrogen was a 0. Here it was a +1. Here it was a -2, -3, +4, +2, +5, and +3. Each and every one of these is different. So that's why it's important to know your oxidation number rules. Let's do one last set of examples with manganese. So we've got manganese in multiple forms here. Let's take a look at just the manganese. So remember, fluorine is always a -1. That means that that's a -3 overall. That means that's a +3. Here we have our -2. That means it's a -4. That means this would have to be a +4. Over here, we have a -2. That's -8. This is a +1. That means this has to be a +7. Over here, we have a -2. Over here, we have a +2. So again, look at this. Manganese can be a +2, a +7, a +4, a +3. It can be a bunch of different charges. But that's how you use oxidation numbers and the oxidation number rules. All right? So if you have any questions, please let me know.